In this video, we're going to give an introduction to symmetric matrices. So I want to begin by sort of outlining the key things that we've talked about in the last few chapters. So in chapter 4, we focused on abstract vector spaces. So on abstract vector spaces. So some of the things that entailed were talking about things like subspaces and coordinates. Subspaces and coordinates. And we also talked about abstract linear transformations. Abstract linear transformations. So in chapter 5, we talked about eigenvalues and eigenvectors. Eigenvalues and eigenvectors. Eigenvectors. So their theory, the theory of eigenvalues and eigenvectors. So that's what we talked about in chapter 5. And then in chapter 6, we talked about orthogonality. So orthogonality. Okay. So I'm going to draw a circle for that as well. And I'm deliberately having the chapters 5 and 6 circles overlap. And I'll talk about that overlap in a minute. But let's first just list out some of the things that we talked about in these two chapters. So in chapter 5, we talked about eigen stuff. So eigenvalues, eigenvectors, eigenspaces. We talked about diagonalization. So diagonalization. We talked about matrices for abstract. Matrices for abstract linear transformations. And in the orthogonality chapter, we talked about things like the dot product, projections, orthogonal matrices. So orthogonal matrices, which are going to show up often in this section. So remember, a matrix U is orthogonal if U transpose U equals U times U transpose, and that equals the identity. So in other words, what this is saying is the inverse of U is its transpose. And we also talked about Gram-Schmidt, which I'll just call GS, and least squares. So I'm not writing down everything that we talked about in these chapters, but this is just a brief list. So what we're going to be doing in chapter 7 is focusing on the intersection of chapters 5 and chapter 6. So we'll be merging concepts from eigenvalues and eigenvector theory with orthogonality. So this intersection is going to form the heart of what we're going to talk about here in chapter 7, which is symmetric matrices. So now let's define what a symmetric matrix is. So if A is n by n, so if it's square, and the transpose of A is the same thing as A, we call A a symmetric matrix. So let's begin with a quick example. Which of the following matrices are symmetric? So to answer this, we need to find the transpose of all of these matrices. So let's do this for part A first. So if I want to form the transpose, we know that the transpose is supposed to interchange the roles of the rows and the columns. So the first column of A will become the first row of A transpose. So that'll be 1, 1 being the first row of A transpose. And the second column of A will become the second row of A transpose, so 2, 2. Okay, and if we compare these two matrices, they're not the same. They are not the same. For example, the number that's in this entry and the corresponding number in this entry, they're different. One of them is a 2 and one of them is a 1. So because A does not equal A transpose, this matrix would not be symmetric. Alright, so let's talk about part B. So part B, if we transpose this matrix, so let's look at our two columns in A. So here's the first column. And that'll become the first row of A transpose. So I'll have A, B becoming the first row. And the second column, the second column of A will become the second row of A transpose. So I'll have B, C. And if we look at these two matrices, they are identical. Because I still have A, B in the first row, and then I still have B, C in the second row in the exact same order. So in this example, A does equal A transpose, so it is symmetric. So this matrix is symmetric. All right, and then finally for this last one, let's do this one a little bit more quickly. The key thing that I want to notice is when you transpose a matrix, when we transpose a square matrix, the items that are on the diagonal don't move. They'll stay in the exact same spot. And the other thing that we need now for our matrix to be symmetric is the elements that are sort of mirror images of each other across this diagonal. So for example, this element and this element, they're mirror images of each other. They all need to be the same for my matrix to be symmetric. So those two entries, the 2's are the same. And then what's mirroring this -3? Well, it's that -3. They're the same. And then what's mirroring this 0? Well, it's that other 0. So clearly here, A equals A transpose. So this matrix is symmetric. This is symmetric. All right. So the key fact that we'll be exploring is that symmetric matrices have extremely useful properties. Let's begin to state some of those. So here is the first property, which I'll state as a theorem. If A is n by n, is a symmetric matrix, then any two eigenvectors that come from different eigenspaces are orthogonal. So this is something that's not true of an arbitrary square matrix in general. The eigenvectors from different eigenspaces are not necessarily orthogonal, but somehow for a symmetric matrix, this is happening. So let's begin our proof by looking at two eigenvectors that come from different eigenspaces. So if the eigenvectors come from different eigenspaces, that means their eigenvalues have to be different. So let's let lambda 1 and lambda 2 be distinct. Be distinct eigenvalues with corresponding eigenvectors, I'll call them v1 and v2 respectively. So that means that v1 goes with lambda 1 and v2 goes with lambda 2. That's what the word respectively means, like in the same corresponding order. So then, let me first identify what it is that we want to show. So what we want to show here is that these eigenvectors of v1 and v2 are orthogonal. In other words, that when we take their dot product, that is 0. This is what we want to show. I'm just going to bubble this. Okay. All right, so how are we going to do this? Well, let's first write down what this first part means. So we know that a times v1 will be equal to lambda 1 times v1. That's what it means for v1 to be an eigenvector with lambda 1 as its eigenvalue. And in the same way, we know that a times v2 will be equal to lambda 2 times v2. All right. So my goal is to somehow show that v1 dotted with v2 is 0. So I'm going to need to introduce some dot products into these equations. So the other thing that I'm going to notice about this is, if I focus on this first equation, for example, if I want to get v1 dotted with v2 into this equation somehow, we can just dot both sides by the vector v2. So let's go ahead and do that. So let's take a v1. In fact, okay, I'm actually going to switch the order of these two sides. Let me write lambda v1 first, and this will be equal to a times v1 on the other side. And now let me dot both of these by v2 on the right. So we'll dot this by v2 on the right, and then we'll dot this by v2 on the right. And the reason why I decided to switch the order is it's going to be easier for me to do computation with this right-hand side. So I wanted to put this on the right so I could use all the space that I have here to continue evaluating this. All right, so we have a times v1 dotted with v2 being equal to lambda, whoops, sorry, I forgot to write lambda 1. Lambda 1 v1 dotted with v2. Okay, so we've seen before that if you take the dot product of two things, in this case dot producting a v1 with v2, that's the same thing as writing the first thing, the first vector, transpose times the second vector. So the first vector in this case is a times v1. When you multiply the matrix A by the vector v1, you get a vector. Okay, so we can rewrite our dot product in this way. So we've seen this a number of times now over the last few sections where we've used this property of the dot product to rewrite it. All right, so now if I have a times v1 transpose, that becomes v1 transpose times a transpose times v2. All right. So the next thing we'll do is I'll use the fact that a is symmetric. And because a is symmetric, that means a transpose is the same thing as a, and then times v2. So this step, one more time, I'm using the fact that a is symmetric, and that means that a transpose equals a. All right. So now what does this equal? So we can continue this down. What does this equal? Well, we have the v1 transpose in the front. And then a times v2, we know from here that a times v2 is lambda 2 times v2. So we have lambda 2 times v2. And now lambda 2 is a scalar, so we can move that to the front. So we have lambda 2 in the front times v1 transpose times v2. And v1 transpose times v2, that is a dot product. So we have the lambda 2 in front. And this is the same thing as v1 dotted with v2. All right, so what have we shown at this point? What we've shown is this quantity, lambda 1 times v1 dotted with the v2, is equal to this quantity, lambda 2 times v1 dotted with the v2. So let's just put those together. So we've shown that lambda 1 times v1 dotted with the v2 equals lambda 2 times v1 dotted with the v2. Okay, so the first one of these, okay, that's better. I meant to highlight it. So the first one of these, let's highlight this in yellow. And the right-hand side, let's highlight that in blue, because that's what we did above. So next what we can do is, let's move everything over to one side and then factor. So if we do that, we'll get lambda 1 minus lambda 2 times v1 dotted with v2 being equal to 0. So we started off this problem saying that lambda 1 and lambda 2 had to be distinct. So this is non-zero. This is non-zero because lambda 1 is not equal to lambda 2. So if that's not 0, and that's multiplying this dot product of v1 dotted with v2, that means that v1 dotted with v2 needs to be 0. And that's what we wanted to show. This shows that v1 and v2 are orthogonal. And that's what we wanted to show. We wanted to show that the eigenvectors that come from different eigenspaces are orthogonal. And now we've done that. So that's an interesting property. It's interesting that when we have a symmetric matrix, that the eigenvectors that come from different eigenspaces are orthogonal. And this theorem will be at the heart of what we state next. So at this point, we are ready to define what it means for a matrix to be orthogonally diagonalizable. and then we'll state a big theorem. So here's the definition. We say that a matrix is orthogonally diagonalizable if A equals P times D times P inverse, where D is diagonal, but now P is going to be an orthogonal matrix. And that means that P transpose times P is equal to P times P transpose is equal to that identity. Remember, an orthogonal matrix is a square matrix where all the columns are orthonormal. And what we've just stated here is an orthogonal matrix is a matrix where the inverse of P is its transpose. So if we use that, we could write this in another way. This is P times D, and then P inverse is the same thing as P transpose. That's true because P is orthogonal. All right, so now we're ready to state the big theorem, which is called the spectral theorem for symmetric matrices. So there's 4 parts to what this theorem says. So if A is n by n, if it's square, and if this is a symmetric matrix, then the following hold. So first, it turns out A will always have n real eigenvalues, counting multiplicity. That's including repeats. The second property is what we just showed before this. Eigenspaces are mutually orthogonal. And what that means is when you take eigenvectors from different eigenspaces, those eigenvectors are going to be orthogonal. And now what's especially interesting about this is property 3 says that the dimension of any eigenspace, so the eigenspace corresponding to some eigenvalue lambda, will always be equal to the algebraic multiplicity of that eigenvalue lambda. So this is true for all eigenvalues. So property 3 actually means that the matrix is diagonalizable. And in fact, something stronger can be said. It turns out, and this is property 4, that A will be orthogonally diagonalizable. So in other words, A can be written in the form P times D times P transpose, where D is a diagonal matrix and P is orthogonal. So this theorem is very powerful. Among other reasons, in general, it's hard to tell just by looking at a matrix if it's diagonalizable or not. But it turns out that if A is symmetric, and it's easy to check if a matrix is symmetric just by looking at it, it turns out it'll automatically be diagonalizable. And even stronger, it'll be orthogonally diagonalizable. So next I want to show that the converse of property 4 is true. So the converse is the statement in the opposite direction. So if A is orthogonally diagonalizable, then A is symmetric. So the actual spectral theorem is actually very hard to prove. But this reverse direction is much easier. So let's talk about why this is true. So if A is orthogonally diagonalizable, that means that A can be written in the form P times D times P transpose. And if we want to show that A is symmetric, we need to take the transpose of A and show that it's the same thing as A. So if we transpose this, on the other side we'll get P times D times P transpose being transposed. And if you take a product of a bunch of matrices and you transpose them, we have to switch the order. So P transpose times D times P, and then put transposes on all of those matrices in the product. But P transpose transposes P, and then we have D transpose, and then we have P transpose. So it turns out that if you have a diagonal matrix and you transpose it, you just get D. It's just the same thing. So I'd encourage you to think about why. It's pretty easy to see, but I might just draw a quick example of a diagonal matrix and just convince yourself that that's true. So notice that what we started off with, A was in this form, is the same thing as what the transpose ends up being. The transpose also ends up being P times D times P transpose. So as a result, this means that A equals A transpose. In other words, that A is symmetric. A is symmetric. All right. So the key takeaway from this is a matrix is orthogonally diagonalizable if and only if A is symmetric. So in the next video, we'll do a number of examples where we check if a matrix is orthogonally diagonalizable. And if it is, then we'll go ahead and orthogonally diagonalize it.